In this recording, we're going to take a look at how enolates can react with carbonyls as electrophiles. So far, we've seen how enolates and enols can react with certain types of electrophiles like halogens and alkyl halides, and they undergo halogenation at the alpha position, and they undergo alkylation at the alpha position. One of the questions is, well, what happens if an electrophile isn't present and conditions are um, possibly right for another reaction to take place? Well, let's take a look at this reaction right here. We have an aldehyde and it's reacting with a base, sodium hydroxide, in water. We already know that we know of a reaction in which you get hydration and you form what's called the geminal diol. And we talked about this in a previous chapter. Now, we also know that this geminal diol, or the equilibrium of this geminal diol, is highly unfavored in that there's no isolable product, and you essentially have aldehyde present. And so the equilibrium is highly favored toward the left. Now we also know of a different type of reaction of an aldehyde where you have a base, and sodium hydroxide certainly is a base, and it can potentially undergo a deprotonation of the alpha hydrogen and form an enolate. We know this enolate is resonance stabilized, so we can have a carbanion character or an oxoanion character, and because of this stabilization, it leads to it essentially leads to the acidity of the alpha hydrogens. All right, now let's think about those two processes. Well, the first one, the hydration, we know is unfavorable. We know it doesn't generate an isolable product, and so nothing happens afterwards. We get an equilibrium between the geminal diol, the aldehyde, and that equilibrium is always shifted toward the aldehyde. However, when the enolate forms, a reaction actually can occur. And we're going to explore this with various types of carbonyl compounds. So let's look first at how ketones and aldehydes can react with their enolates. Now, like we just saw, when sodium hydroxide is added to an aldehyde, an equilibrium is established between the aldehyde and the enolate. And if we understand that equilibrium process, then we can kind of start to understand what's going on as a potential reaction. So I have here I have acetaldehyde, and of course I've just highlighted one of the alpha hydrogens, and I have hydroxide. A reaction ensues in which the hydroxide removes an alpha hydrogen, and I establish an equilibrium between the aldehyde and its enolate. Notice also I generate water. So the entire reaction is the reactants are aldehyde, acetaldehyde in this case, and hydroxide, and the products are enolate and water. And if we understand the complete equilibrium conditions, then we can get a feel as to what's actually in solution at equilibrium. Now, to do that, we have to think about pKa's. So the pKa of acetaldehyde we know is 16.7, and of course the pKa of water is 15.7. And this is simply an acid-base equilibrium. If we know the pKa's, we can approximate the equilibrium constant for this reaction. So there's a difference in pKa of about 1, which means that there is a tenfold difference in the concentration of products to reactants. And of course, since acetaldehyde is the weaker acid, that equilibrium is going to be favored toward the left, right, toward reactant formation. And so we get an equilibrium constant that is about 0.1. Now, what does that mean? Well, it means that essentially for every one enolate, you have about 10 aldehydes present, right? So for every one enolate, you have 10 aldehydes present. But let's think about what's now in that solution. We have aldehyde present, but we also have enolate present, and it's not an insignificant amount of enolate that's present. We've seen with enolates that enolates behave as nucleophiles. And now in this particular instance, when I'm using sodium hydroxide, a weaker base than we've seen before with LDA or sodium hydride, now I have an electrophile present. So in this reaction, there is an electrophile present, and it is the aldehyde of the corresponding enolate. And therefore, these two things are going to react. Now, how do they react? Well, the enolate attacks the carbonyl, and you get an addition product. How do you draw that addition product? Well, it looks like this, right? So notice on the left-hand side, that's the portion of the aldehyde, and of course, when we undergo a nucleophilic addition, the carbonyl bond breaks, and you form an oxo anion, right? So that's the oxo anion, and now I've connected it to the alpha carbon of my enolate, and of course, there is a carbonyl there of the aldehyde present. And now this anion can react with water and undergo a proton transfer. So we get protonation of that of the anion, and we generate a species that looks like this. So if we think about what this type of structure is, on the beta carbon we have a hydroxy group relative to the aldehyde. And so these are called beta hydroxyaldehydes. And oftentimes we abbreviate that as simply an aldol, right? It's an aldehyde and an alcohol combined, but it's a beta aldol, which is very important because what happens next is that at higher temperatures, elevated temperatures, and sometimes those temperatures can be room temperature. So when I say higher temperatures, I simply mean at a temperature that's feasible for the reaction to continue, then a dehydration occurs. And the reason for that is because the aldol that we produce still has acidic hydrogens on it, right? The alpha hydrogens are still acidic, and we're still in basic conditions because notice we on the top there we regenerated hydroxide. So now that hydroxide can come along and remove another alpha hydrogen, and we generate another enolate. And of course, this enolate is also resonance stabilized. So I can draw a resonance structure where I promote those electrons to the carbonyl, and I generate an oxo anion of the enolate. Now, this is a very particular conditions. Whenever you have a stabilized anion, and adjacent to that you have a hydroxyl group. Now typically the hydroxyl group is a very poor leaving group, but in this particular circumstance it actually is a relatively good leaving group. And we call this an E1CB. E1 means unimolecular elimination. So the rate determining step is in essence the formation of the enolate, and then the conjugate base of water, so CB stands for conjugate base of water, comes off. And we can show that by donating a pair of electrons back to form the carbonyl from the enolate on the right. And then the pi bonds move between what is the alpha and beta carbon, and the OH is lost. And this is the product that results. Notice hydroxide still comes off. So theoretically, hydroxide is a catalyst in this reaction. Now, this particular product has a double bond between the alpha carbon and the beta carbon, so it's called an alpha-beta unsaturated aldehyde. Right? So we're going to see that this reaction can actually occur in acidic conditions as well. So we saw basic conditions, and this can occur in acidic conditions just as likely. And as a matter of fact, it forms the unsaturated aldehyde much more rapidly than in basic conditions. And we're going to see why in just a little bit. Now, in acidic conditions, we have slightly different variations. Obviously, we have an acid instead of a base, and so the first step, we always should be thinking in acidic conditions, we have a carbonyl, the first step is going to be proton transfer. And so that's going to result in a protonated aldehyde. And we've seen this type of reaction before, and we know this occurs very fast. Now we've also seen that in acidic conditions, water can attack the carbonyl, and you get a geminal diol. But again, the equilibrium resides mainly at the aldehyde. So another possibility is that the water can remove an alpha hydrogen. And so when it does so, we form this, right? And this is an enol. Notice in basic conditions we form an enolate. In acidic conditions we form an enol. Okay, now, and again, equilibrium isn't quite favored here, but what we have to think about what's in that solution. In acidic conditions, what do we have in solution? Well, we have our acetaldehyde, but it's going to be protonated, and we have our enol. And the enol is a good enough nucleophile now to attack a protonated acetaldehyde. And that's exactly what happens. So the oxygen reforms the carbonyl, the alkene of the enol attacks the carbonyl carbon, displacing the carbon-oxygen bond. And the result looks like a structure that's very similar to the aldol addition in basic conditions, but slight little twist. Number one, we don't form an alkoxide, so there's no anion present. We actually have a cation present. So we generate an OH, and now the carbonyl is still protonated. And now all we have to do is, with water, deprotonate that carbonyl, and we generate our aldol. So now I have my aldol, and of course I regenerate my acid in the process. All right, now what happens next? How do we get to the alpha-beta unsaturated aldehyde? Well, notice we have two oxygens here. We have an alcohol oxygen and we have a carbonyl oxygen. And either one of them can get protonated, certainly. We've seen both of them get protonated. But the alcohol is certainly more basic. And the reason for this has to do with hybridization. The alcohol is an sp3 hydrogen, and the carbonyl oxygen is an sp3 oxygen, excuse me, and the carbonyl oxygen is sp2. So sp2 atoms hold in their electrons tighter because they have more s character, and therefore the OH is more acidic and it will get protonated. Now, when it gets protonated, I have formed a good leaving group. And now I can simply undergo, this is a relatively straightforward E2 mechanism where water can come along, remove a beta hydrogen, which is the alpha hydrogen relative to a carbonyl, and then we generate an alkene with the loss of water, and I have my alpha beta unsaturated aldehyde. And this certainly occurs very rapidly. And because of it, it actually drives the equilibrium to that product formation. So even though at the top we see that the enol is not favored, once a reaction occurs between the enol and its protonated aldehyde, um, then that equilibrium resides toward the product. And of course, it becomes essentially a sinkhole, and you get more and more product, and it occurs very rapidly. Okay? And that's basically how, why these reactions take place, because once you form that alpha beta unsaturated aldehyde, um, it drives the reactions forward in both basic and acidic conditions to form our product. Typically, basic conditions are a little bit slower, and acidic conditions are a little bit faster, simply because of that elimination process, right? So let's see if we can figure out how to predict the product. These can sometimes be a little bit tricky, and you have to really pay attention to how many carbons you have and the carbon skeleton that you're actually joining together, right? So the first reaction we're going to take a look at is reacting butanal. Now notice I have two butanals, and sometimes you'll see the two there and sometimes you won't. For this purpose I'm going to put the two there, but understand that if you don't see that two, you just see an aldehyde in sodium hydroxide, then you should know that it's going to form an equilibrium between the aldehyde and the enolate, and that enolate is going to be present and the aldehyde is going to be present. All right, so how do I predict the product? Well, when we're starting out doing these types of problems, I highly recommend drawing the enolate out, right? So I'm going to draw it in blue so I can kind of distinguish between my aldehyde and my enolate. So now I have this equilibrium that exists between the aldehyde and enolate, and I know the enolate is a nucleophile and it's going to attack my aldehyde carbonyl and displace that carbon-oxygen bond. All right, so how do I draw the product? I always start with the carbon skeleton of the aldehyde. For me, it makes it a little bit easier. And so I draw the structure, and I'm simply going to start, right off the bat, convert that carbonyl into a CO single bond and have the oxygen protonated. So I have that COH. And now I can start to think about the connectivity. So it's added, the alpha carbon of my enolate has added to it, and that alpha carbon has an aldehyde coming off of it, and it also has an ethyl group coming off of it. Right? Can you see that? The alpha carbon has an ethyl group and an aldehyde. So I simply draw the alpha carbon, I draw the aldehyde coming off of it, and I draw the ethyl group coming off of it. And that's how I form my aldol. And of course, upon heat, I can get dehydration. And so you see that that dehydration always occurs between the alpha carbon and the beta carbon. It has to be between the alpha carbon and the beta carbon because the alpha carbon has the acidic alpha hydrogens. I can't draw it toward the gamma carbon because those are not acidic hydrogens, right? And there we have our alpha beta unsaturated aldehyde. Sometimes these are referred to as enones or enals in this particular case. All right, here's another example. And so again, how do you start this problem? You should start it, especially when you're learning this, drawing the enolate. So now I have my aldehyde, I have my enolate. I know the enolate's going to attack that aldehyde, displacing the carbon-oxygen bond. So to draw my product, I start with the basic structure of the aldehyde. I convert the carbonyl into a COH, and now I'm going to add that alpha carbon to it, and it has an aldehyde on it, and it has a benzene ring on it, right? And then, of course, when I heat this up and think about the product that results from it, again, I'm going to form a double bond between the alpha carbon and the beta carbon in which the hydroxide is attached to. And therefore, the double bond goes right there. And that's my product that forms. Now, these are, these all, the reason why I form a double bond there certainly is because there are still alpha hydrogens present. So let's look at an example where upon aldol formation you don't get any, there aren't any remaining alpha hydrogens. So here's an example where I have methylbutanol, 2-methylbutanol, and of course you notice on that alpha carbon there's only one hydrogen present. So we certainly can get addition occur. We're going to form our enolate. We can form the enolate, and that enolate looks like this. And of course we now know that that enolate is going to attack the carbonyl, and we get an addition reaction. Again, we draw the aldehyde carbon skeleton with an OH, and then we draw the alpha carbon attached. It has the aldehyde coming off of it. What else does it have coming off of it? Well, it has a methyl group and it has an ethyl group, right? So in this particular case, there are two substituents coming off of that alpha hydrogen. And the key also is there are no more alpha hydrogens. And therefore, I can't undergo elimination, right? That E1CB elimination can't happen because there are no alpha hydrogens. And a common mistake is that students go, oh, well, I know I can't draw a double bond there because that alpha carbon would have 5 bonds to it. So what am I going to do? I'm going to draw a double bond on the other side. Don't do that. The product is simply this, and there's no condensation that occurs. You simply form the aldol, and that's all you get is the aldol. So let's think about this retrosynthetically. Well, one of the key things is that if you see a beta hydroxyaldehyde or an alpha beta unsaturated aldehyde, you better think aldol condensation, okay? So this is the key in recognizing the functional groups present. Always look, if you have an aldehyde, always look to see if there is a double bond at the alpha beta position or a hydroxy group at the beta position. And if so, that should be a red flag to you that product happened through an aldol condensation. So let's take a look at kind of how you work backwards retrosynthetically on an alpha beta unsaturated aldehyde. So here I have an example of an alpha beta unsaturated aldehyde, right? We have an aldehyde, and between the alpha and beta carbon we have an alkene. And so that's our unsaturation. So one of the things that, the first thing that I do, again, in terms of, I recognize, okay, it's an aldol condensation reaction. So what aldehyde reacted, or aldehydes, I always have to make sure, because sometimes there are situations where I can have a mixture of aldehydes. We'll get into that a little bit later on. But what happens, what aldehyde was used in producing this particular product? Well, the first thing that I do is I start with the beta hydroxyaldehyde, right? Because I know when I was drawing the products of aldol condensation, the first thing is that I drew kind of the carbon skeleton of the aldehyde, and I converted the carbon-oxygen double bond into a COH. So that COH that carbon is where that point of attachment lies. So retrosynthetically, I'm going to break it right there. Um, and I'm going to convert the alcohol into a carbonyl. And so notice I get um, I get this particular aldehyde structure, and if I draw what's on the right there, I get the same thing. So I know that this is an aldol condensation of this would be 2-methylbutanal, or I'm sorry, 3-methylbutanal, and that's the product that I get from it. So now I know that um, that this product on the left comes from the aldehyde on the right. And this is something that sometimes you kind of have to work at. So one of the things is, practice and see if you can draw just alpha beta unsaturated aldehydes. They don't necessarily have to come from the same thing, and see if you can envision what aldehydes they're derived from. Okay. All right, so we've taken a look at aldehydes, but we haven't looked at ketones yet. And in general, ketones don't readily produce aldol products in basic conditions. Because like hydration, if you remember when we talk about hydration, the equilibrium of ketones in hydration is even worse than that of aldehydes. And so the ketone itself is not very electrophilic, right? And that's the reason for the equilibrium being so shifted toward the ketone itself. Now, and oftentimes, we say that they don't readily occur, but I mean, they do still occur. You just oftentimes have to use a lot longer reaction times and higher temperatures to do so. So you're going to see some reactions of ketones that are similar to that of aldehydes, but just understand those reaction conditions are a lot different, a lot longer, and typically have higher temperatures. Now, in acidic conditions, where that dehydration readily occurs, you can get formation of an alpha beta unsaturated ketone because that ketone actually pulls the equilibrium to the right. And therefore, um, it, aldol condensation, notice I say aldol in quotes because we have a ketone here, so it's a ketol of condensation actually occurs a little bit better in acidic conditions than it does in basic conditions. But again, it still can occur in basic conditions. So here's an example of acetone in sodium hydroxide. And of course, acetone has an acidic hydrogen, and so it can form an enolate. And now that enolate can react with acetone. And it can undergo an addition reaction, just like we saw with the aldehyde. However, this is the slow process, and the reason for that is because acetone, like other ketones, is stabilized by its alkyl groups, right? And what happens is the electrophilicity of that carbon decreases drastically. So this is the slow step. That addition process is the slow step. It can occur, and um, so you can get an addition product. And how do we draw the addition products? It's a very similar to that of an aldol product, but keep in mind now we have two R groups coming off of that carbonyl carbon, not just one R group. So in this particular case, I have two methyl groups. I'm drawing one of the methyl groups kind of up so that I can now come in and draw my alpha carbon with the carbonyl attached, and of course there's a methyl group attached. So you can see that where the enolate has added to that carbon. And of course, now I have a beta hydroxy ketone, and that beta hydroxy ketone, if I heat it up enough, I still have acidic alpha hydrogens, and it can undergo an elimination. Um, and we can look at another example. Here I have cyclohexanone in basic conditions. And cyclohexanone, if I draw out my enolate of cyclohexanone, this is the enolate of it. And of course, the enolate's going to now attack the carbonyl carbon, displacing that carbon-oxygen bond. So when I'm drawing the product, I can draw the backbone of the cyclohexanone with the OH coming off of it. And now I have to add that carbon, that alpha carbon on there. So I have to, be a little bit careful because the alpha carbon is part of this ring. And so it looks like this, right? So notice I've created a bond between that, what was carbonyl carbon, and the alpha carbon. And then, of course, adjacent to that's my carbonyl, and it's part of that six-membered ring. Now when I heat this up, I get elimination. So I form the double bond between the alpha carbon and that beta hydroxy carbon, and I form that alkene. These are called enones, alkenes with a ketone. So enones, you'll often hear them called. All right. Now I said that ketones don't, they react very slowly in basic conditions, but they will react fairly readily in acidic conditions. And the biggest thing between basic conditions and acidic conditions, again, is the mechanism and the understanding what the nucleophile is and what the electrophile is. So in acidic conditions, obviously, the electrophile is not the ketone, but it happens to be a protonated ketone. The ketone is going to be protonated and increase the electrophilicity of the carbonyl carbon. The nucleophile is not an enolate, but instead is the enol of the corresponding ketone. And this would be the enol of the ketone. So now that enol can react with the carbonyl, and we form an OH group. And so this is our product. So notice that that COH has a methyl group coming off, and then it has that phenyl group coming off of it. And then I can draw my the enol portion of it, the alpha carbon adding to it. And of course, in this particular example, the alpha carbon doesn't have anything else attached other than hydrogens. And so, of course, I can get elimination here. And I really don't even have to heat this up because it's acidic conditions, and elimination will occur readily. And I just noticed that I lost a carbon. So keep in mind there should be a carbon here, and I'm going to draw it in right there, right? Okay, so this is the product that I get from the addition reaction of a ketone. And that's basically how aldol reactions work. Sometimes they're a little bit tricky, but if you play with them just right, you can start to see how the puzzle fits together, and that's certainly the key. And once you start getting them, it's kind of fun to see how they come together.